It's my pleasure to introduce Mikołaj, who will tell us about infinitesimal containment and sparse factors of IIDs.
Thank you. So it's a pleasure to be here. I was a postdoc 5 years ago, so it's super nice to come back. So thanks for the invitation. This is my first talk on this subject. So it will be kind of experimental. My first talks I always try to cram too much into the talk, and then next talks are more balanced. But okay, so maybe I'll start by telling you what kind of problem I'm interested in. Then I'll motivate it using some problems that you might be interested in. And then we'll delve into details. So the problem is like this: you have a gamma, which is a countable group. I should write bigger. Is this group big enough? And this gamma acts on some probability measure space, x mu, and this is a probability measure preserving action. And this probability measure preserving, I will use abbreviation PMP. Okay. And what I want to understand are the dynamics of small subsets of X. So how gamma kind of mixes small subsets of X. And let me make this even more precise. So suppose I have a subset U in X. Measure of U should be small, let's say smaller than some delta, which is a small number. And I'm interested in the geometry of the set of gammas. I'll call them the set U, iota U of X. This is a set of gammas, gamma, such that gamma inverse X is in U, and X is an element in big X. So it's kind of set of return times. I put this minus here for the following reason. I want the map iota U be an equivariant map from X to the space of subsets. So if I set up my definitions correctly, this thing is equivariant with respect to gamma action. Everything is nice. Actually, gamma action on the left. And what I'm mainly interested in would be kind of what is the geometry? What is the geometry of iota U X for a typical X in U? So I look at kind of set of gammas which take my point of view back to U. And let me give you kind of several motivating examples how those sets might look like. I mean, in this generality, you can imagine that you can kind of make pretty much everything, right? But turns out that when you fix X, sometimes this geometry of those sets is quite restricted, especially if they're small. And this is not immediately obvious. So let's do some examples. First example will be, for example, we can take X to be 0, 1 power gamma. Mu can be a Lebesgue measure of 0, 1 raised to power gamma. And then I can take set U, which is, for example, the set of words our configurations in the space such that we think of those as functions from gamma to 0, 1, so that omega 1 is, let's say, less than delta. So then the measure of this set U is exactly delta. And this set of return times, iota u for x, is just Bernoulli random subset of gamma with parameter delta conditioned on containing identity. Right, because I kind of want to look only at the sets where x is in U. That's why I have this conditioning. One is in the set. And the reason kind of for that, I mean, you could look at all x's in X, but because we're interested in sets U which are very small, if you take typical X which is not in U, you will not see any returns for a long time. Large balls around identity. So we kind of restrict our attention to just X's that are in U. You can kind of, this example is not super exciting. You can make example 1.5. When you take, if you take any U inside this product space, then the resulting set, we call the resulting set a factor of ID subset, iota u x in x u random. It's called a factor of ID subset. And study of factor of ID subsets or more general structures like colorings, etc., is like a large area in itself. You can there are many interesting questions. What kind of subsets you can get as a factor of ID? Maybe just to name a few, you can look at, I don't know, you can endow gamma with the structure of a Cayley graph. You can look at independent sets which arise as factors of ID, connected subsets that arise as factors of ID, and there are many kind of works about them. But now let's move for a moment away from Bernoulli shift and consider more maybe familiar situation where, for example, we take gamma which is equal to SLBZ, and our space will be SLD ZP, so this is p-adix. And then we can, for example, choose U to be the set of all matrices gamma and SLD ZP, such that gamma is, I'll write it like this, gamma is a block matrix, so it's inside SLD minus 1, 1, 0 here, 0 here, modulo p power n. All this makes sense. And when you take a set U like this, you look at the set of typical returns, then this iota u x, it looks like, I mean, it's not exactly equal, but it looks like SLD minus 1, 1. Supposed to be Z here. As n goes to infinity. So that means that when I make this power of p bigger and bigger, this set U is kind of a smaller and smaller neighborhood of a coset of a closed subgroup. And when we look at set of returns to this set, it kind of mimics the analogous subgroup of SLBZ. And maybe what I could give as an exercise or question for board, can you model in this way the subgroup SLD 1Z1 as this return set inside Bernoulli shift? So I guess the Algati group is SLDZ. So we can model it inside p-adics. And it's not clear if you could model it inside Bernoulli shift, but if you think about it a little bit, it turns out that ergodicity of SLD minus 1Z acting on the Bernoulli shift of SLD implies that you actually cannot do this. So there are some limitations to the geometry of subsets of gamma that you can model as return sets in an action. Okay, and so my main result will be about Bernoulli shift. It turns out that the geometry of the sets that you can model when this measure of U goes to 0 is very restricted. But maybe before I state this result, I want to kind of motivate why we might want to look at this problem in the first place. And the motivation comes from question about rank gradient. Here, so yeah.
When you say model this set, you mean that iota U becomes thinner and thinner, and so probably around every average point will be emptier and emptier. Do you condition that the identity is in?
I always, unless I say otherwise, like here, I always condition on the X to be inside U. So identity is always there. Mm-hmm. And as you say, like as the set gets thinner, it could happen that identity is the only thing that we see. Mm-hmm. But for example, here I managed to kind of keep an orbit of a subgroup inside. Mm-hmm. Right, and the kind of the key fact that I use here is that this subgroup, it does not act ergodically on this space. So I can kind of take its orbit, thicken it a little bit, and I can approximate the subgroup as a return set. And this return set is always probabilistic, but I mean that in some probabilistic sense I approach to this set. Right. So, yeah, any other questions? So motivation comes from the following problem. And this is a problem about a number of generators of a group. And I'll just start with a simple group. So I'm in a group. So gamma would be SL2 Z of I. This is a lattice. But you can actually ask this question for any lattice in SL2C. Let me define this rank of a group as the minimal size of generating set. Then we can ask a question, okay, given a sequence of subgroups, gamma index n inside gamma finite index. What is the rate of growth of the rank? And well, we should expect that rank grows as subgroups get more and more complicated. That's what usually what is usually happening. So we want to normalize it. So in particular, we look at the limit as n goes to infinity of the normalized rank gamma n, normalized by index of gamma n and gamma. So what is it? It doesn't even converge. So maybe some context. Okay, so this question, the question about rank growth is very popular in measured group theory. And I think that this group might be one of the hardest open cases, or no, hardest cases of this question. At the same time, we motivated somehow by considerations in number theory and so on.
Is this something you could check empirically on the computer? What is the size of the smallest generating set? I give you.
Sure, somebody did it, but I don't know. I think
Can you do it if I give you some kind of subgroup of gamma n, some congruent subgroup of gamma?
Find the generating
set?
Maybe it's hard to. I'm not qualified to answer that, but if I had to guess, I think it's in rank one groups like this. It's hard to check if you found generating set, especially if you're kind of looking for small ones. It's in higher rank.
For free groups, it's easy, right? That's the usage trial, and that's like upper bound, like that's the trace.
Exactly. There are classes of groups where we have exact formulas for the rank.
Things are properly in hyperbolic three manifolds and understood. This kind of decidability question. I mean, if you have products, like if you want to know whether a certain set of elements generate the whole group or not, that's undecidable in like SL2 cross SL2Z.
Oh, so it's
yeah, there's no decision procedure to given a fixed number of elements and decide. Yeah, that's follows from the. I forget her name. What's a student of Novikov's dad?
I think people were looking at growth of mod p Betty numbers for those groups.
No, so there's Lakenby's work on growth on this rank, but that's coming from abelian stuff, right?
Yeah. People look at growth of torsion first homology, and those things have numerical evidence that can kind of maybe prediction of predictions. So those questions are kind of related to this one. So if you take a limit as n goes to infinity, maybe I'll pick n. So for those who know, I'll work with congruent subgroups. I'll just write in a moment what that is. Not rank, but I'm looking at.
But you're looking at billionization.
I'm looking at torsion part of H1 of this thing. Z torsion. Maybe this deserves a new line. So I like it here. So for NAP prime, we can ask for a limit as n goes to infinity, n goes to infinity of the dimension over Fp of the first homology group of this group gamma n coefficients of P, normalized by the index. And we don't know what that is at the moment, but the numerical evidence suggests that it should be 0. But there is another problem where you look at not just single prime, but all primes at the same time, and you can look at size of torsion homology with Z coefficients, and then this grows. So we don't ask about dimensions, but the size should grow exponentially fast.
Q, the cohomology, that's true.
Right. If you replace this by Q, then it's true and it's proven.
Right.
But for FP, we don't know. What else we can ask? we can also limit as big n goes to infinity of the logarithm of the size of torsion subgroup H1, gamma n with coefficients in Z. Torsion subgroup divided by the index. This we also don't know what it is, but the numerical evidence suggests that maybe it's positive. And the constant is worked out. But
Bergeron and Venkatesh.
those problems are considered extremely hard in this area. Nobody has, I think, right now any solid idea how to. Okay, maybe I'm. Those problems are probably harder than this one.
Yeah. But people are talking about gamma lattice in what groups?
Hyperbolic lattice in SON1, you can ask. I think for all SON1s for n is at least 3, those problems are open and hard. Mostly more classical arithmetic groups. I promise I'll explain what gamma n is. So gamma n is the set of gammas in gamma SO2 Zi, set that gamma is congruent to 1 mod n. So we will look at those sequences. Okay, so in particular for those sequences of subgroups, we would like to know what's the growth of rank. I think contrary to those cases where there are some expectations, here experts are divided. What should be the answer? Is it 0 or positive? You have non-trivial proportions of people who think either way. I personally think it's positive, and maybe this talk will give you some weak heuristic why it should be positive. Okay, so right. So you have this question about growth of ranks. I need to add more context. So more context. In general, you can see that I asked about sequences of arbitrary subgroups of finite index. Here we asked about particular sequence of subgroups, but in general, we don't know if those limits, if they exist, they are dependent on the choice of subgroups. So for gamma, which is equal to either a free group or pi1 of the surface, this limit as n goes to infinity, maybe as index goes to infinity. So I can just take any sequence of subgroups, if this is going to infinity, limit of rank of subgroup divided by its index, and this is the constant, and this constant is independent of the subgroups. As long as the indices go to infinity, this limit doesn't depend on the particular sequence. Turns out that higher rank lattices, same thing is true. Okay, so here this C is bigger than 0. For high rank it will be 0. So for gamma lattice, a torsion free lattice in a simple higher rank group G, we have that limit as we look at sequences of subgroups of indices going to infinity. rank of a subgroup normalized by the index is always exists and it's zero. Again, independently of the sequence. So this is a theorem that myself, Sam Belli, and Amanda Wilkins. From 23. So we had to work relatively hard for this. It's not here. It's simple.
The rate?
No, it doesn't exist yet. But if I were pressured to guess, I'd say that the rate is log, some small power of log, some power of log of the index, like log rank minus 1/2. Log of the index power rank minus 1/2.
And this is related to what Peter explained to us, this that the cost of these groups is one.
Yes.
Parser.
Yeah, exactly. That's kind of deduced. This result is deduced from some measured group theory result. And I'm going to tell you a little bit about cost. Yeah, but if you, our proof in principle could be turned into proof that gives you some weak rate. But it's kind of, I think people believe that the rank of higher rank of concurrent subgroups in higher rank semi-simple groups grows like power of log of volume, and this is way off from what we can prove. So you probably need some smart number theory or something to get the optimal rate. But it's kind of frustrating that it's, while we have some tools to get upper bounds on the rank row, we don't really have many tools to lower bound. Now, those questions about growth of rank, they can be understood with the help of some conjectures in measured group theory. So now I'll tell you what cost is. And the action. So again, suppose that we have a gamma countable group acting on some probability measure space X mu. And what I'm going to define kind of is it's like a size of generating set for this action in some sense. So a graphing for this action is a collection of maps. So those will be maps phi I. They go from some domain UI to X, where UI is subset of X, not necessarily everything, so they can be defined partially. All those maps are measure preserving. And satisfy two conditions. So first condition is that phi I of X, whenever this makes sense, so whenever X is in the domain, and this is always contained in the orbit of X. So it's contained in the orbit of X by gamma. And the second condition is that we are supposed to be able to jump between any 2 points in the same orbit by taking kind of maps from this set. So for almost every X in X and every gamma in gamma, I can find a collection of steps. So there is a sequence of indices I1, ID, which are in this index I. Some symbols epsilon1, epsilon d, which are plus minus 1, such that gamma x can be written as composition of phi's and their inverses. So phi ik or epsilon k of phi ik minus 1, epsilon k minus 1, and so on. Phi epsilon 1 I1 of x. Okay, but that's best to think about visually. So you have some point x, you have some point in the orbit which is gamma x, and I'm supposed to take kind of arrows from this set of maps, which take me from x to gamma x, and I can take inverses. I can take inverses. So graphing, for those who maybe are familiar with measured group theory language, this thing means that the graphing generates the equivalence relation given by the group action. So orbit equivalence relation.
So the I, the capital I is just
Some index set which is countable, and so you should think that okay. Yeah, but they don't have to be defined everywhere. So you put a collection of arrows on your measure space in such a way they're supposed to jump between any points in the same orbit using only those arrows. And I'll give examples how this can lead to some savings on the number of arrows. Because you can, for example, take generating set of gamma, and your maps will be just actions by elements of the generating set, and this will be a graphing. But sometimes it's highly not optimal. You can delete some of the arrows, and still it's a graphing. Yeah. Build this picture here. So I have my space, which is x. And yeah, I think of it as putting collection of arrows in space in such a way that for every 2 points in the same orbit, I can take those arrows and get from one to the other. X, gamma x. Okay, and then I define cost of the action as the infimum over all sums over all graphings. So this is all graphing. So by graphing sum over i's, the index set measure of ui. So I take sum of the measures of the domains of my arrows. And this is interpreted as kind of minimal average number of arrows. Arrows needed to generate orbits. Okay. And how does it connect with the discussion about this run growth? So it turns out that there's a theorem that kind of connects them. And this theorem says that if you have a sequence of subgroups gamma n in gamma, which is nested, so all of them are finite index, gamma n plus 1 is a subgroup of gamma, and then we can form an inverse limit of finite actions. So we can take x equal to the inverse limit of actions of gamma on the set of cosets. So maybe instead of defining it, I'll just tell you what it is in some interesting one interesting case, and you will be able to fill out the details in your head. So, for example, when gamma is equal to SL dz, and gamma n is equal to the principal congruent subgroup level p power n, which is defined as before. Same definition. So we take only matrices that are congruent to 1 modulo p power n. Then this inverse limit of actions on cosets is exactly SLD ZP. So it's kind of complete, some kind of profinite completion. In this case, it's a group, but in general, it doesn't have to be a group. But it's always is some kind of action on profinite completion modulo closed subgroup. So it turns out that the action on this, and this always comes with some probability measure, mu. So I can actually take x mu. So it turns out that the cost of this action encodes the run gradient. So cost of action of gamma on this inverse limit is equal limit as it goes to infinity of the run gamma n divided by the index. So you can attack those questions about run gradient using some results about cost. This is just a translation, but dictionary, but it is actually useful to think about it in this measured way.
So one direction is obvious and the other direction is a proof for.
Estimate that cost is at most this is obvious, while the other direction is a proof. It kind of tells you that you can cheap graphings of this thing lead you to small generating. So this is not obvious. This requires a proof. Can be done. So I wanted to give you a few maybe more results and conjectures about cost. Here.
So the two results here under this limit are just proved by cost, by using some different costs.
I think except those simple cases, all of the results I'm aware of.
So what gives you the zero here?
I'm sorry, I forgot about this. Cost -1 is equal to limit. Yeah. There is this annoying thing that cost. Okay, yeah, it's cost -1. So the zero here is we just proved that all actions of higher rank lattices have cost 1. And we recovered this statement of rank growth.
And for that, what do you use what are you using about the
Here
in your proof that it's 1?
We are
Just trying to understand what kind of using any.
the key phenomenon that we use there in some way is that if you take two horribles in higher rank symmetric space, there is an infinitely long interface where they are bounded distance from each other. And this is not true for rank one. For rank one, there is a closest point where they are closest to each other, but as you move away, distance increases, while in higher rank, you always have this kind of interface, infinity long interface, where the horoballs are horospheres are bounded distance from each other. And this is just explained by the fact that, well, it's kind of follows from Buhat decomposition.
So you don't need any fancy rigidity, high rank rigidity.
Not really. The high rank assumption comes from from the fact that two generic parabolics intersect in a group that is more than one dimensional.
Yes.
But it's not so clear that it's completely unrelated to, let's say, Margulis normal subgroup theorem proof or things like that. I think it's not, it has some ideas which seem in common.
Yes, because older proofs of special cases of this theorem, they used chain commuting unipotent subgroups, which are also used in Margulis superrigidity. But we don't use any, our proof does not rely on superrigidity in any enough way. Also, there are superrigid groups where our methods fail.
I mean, are you using any of these theorems that in these high rank, you mini Schramm converging to universal cover? Is that you?
Yes.
That you have to be converging.
We use them to get this statement, but what we do in the paper is actually showing if you have the sequence of quotients that Bay Schramm converge, then rank is sublinear in volume. But this result doesn't rely on techniques used to prove Bay Schramm convergence. So you can take them as a black box and then get this result. Yeah. But so far none of the techniques that I kind of bound the cost from above, none of them works to show that in rank one lattices you have cost one for all actions. And for all we know, this might not be true. Right. Okay. I have 20 or 10 minutes left. It's, I don't know, it's full hour or 50 minutes.
No, full hour.
Oh, okay. Right. So, let me state what fixed price conjecture. What does it say? And maybe question / conjecture. Again, there is no agreement whether this should be a conjecture or just question. This is a question motivated by lack of counterexamples, but not any kind of deep reason that it should be true. So suppose, does the cost of PNP action, maybe is the cost. Is the cost constant?
What setting are we now?
Sorry?
What is the setting now?
Arbitrary countable group, arbitrary PNP action.
Oh, well.
But we just ask for essentially free actions. So for essentially. So essentially free means that no non-trivial element of gamma fixes a positive proportion of the space. So almost every point has trivial stabilizer. That's what we need.
Constant as it depends on gamma.
Right.
Or fixed gamma.
For fixed gamma. Because well, maybe all example, we don't know counterexample to this. And that's, I think, that's the motivation for this conjecture. If it is true, it would have powerful implications because if you're interested in the question of rank gradient, you could for free swap this action with any other action. right? And it could be the case that for some actions it's easier to show those cheap graphings of cost close to 1 than for this original one. We also know what is the worst action for this equation. The theorem by Albert Weiss. Yes. That which says that the cost is maximized for gamma acting on its Bernoulli shift. So this is probably the PNP action with maximal cost.
Does it really depend on the base? So like is 0, 1?
It doesn't depend on the base. As soon as the base has at least 2 elements. Yeah, this is kind of okay. This is the richest action because you could put any probability space to gamma. Yeah. And all of them are isomorphic. They're atoms. But I think it's not so hard to show that this is equivalent to that this has the same cost as 2 elements at 0, 1 over gamma with equal measures of 0, 1. So this theorem kind of implies that, for example, corollary of this theorem, if cost of the Bernoulli shift is 1, then gamma has fixed price. And this relies also on the fact that cost is always lower bounded by 1. For all essentially reactions. By infinite groups. Because this just, so you can make this observation on your own. If you want to connect every point to every other point, then every point needs to have at least 1 arrow connected to it. So, right. So this is also kind of a pathway to fixed price 1, and this is in fact how we prove this theorem. So we didn't have to do this for all actions. We just needed to do this for 1 action. Okay. Now let's go back to this nice group SL2ZI. Because I want to give you an example of an action where we can compute cost, and it's 1. So yeah, again, gamma will be, maybe I'll take, I think I want to take gamma, which is pi 1 of M, where M is compact hyperbolic manifold. Okay. Then, so just like for this group SL2ZI, this kind of corresponds to a non-compact hyperbolic manifold. The question about rank gradient of this group is wide open. We don't know if it goes linearly in the index or not. But what we do know is that this group will always admit actions, PNP actions, which are free, essentially free, which have cost 1, and the construction of such actions relies on fibering. So let me give you an example of this action. So by angle, passing to finite index subgroup. We can replace gamma by finite index subgroup, which has the following decomposition. So it's n semi-direct Z, where n is a surface group.
This much more than prosperity number positive?
Yes,
Much more.
I think it's much more. Because
Yeah, it's much less, right?
and it's finitely, it's kind of, if you have some map to Z, there's no reason to expect that the kernel is finitely generated. Here it is finitely generated because it's a surface group. So this follows from a virtual fine-grained theorem. And once we have this thing, what we can do is that we can take any PNP action of gamma on X mu. I can let rho be the map that goes from gamma to gamma mod n, which is Z. So, and I take any other action and some action gamma on Z tau that factors through rho. So we only act by Z. So n acts trivially. And then my new action will be the product action. So I take, this will be the, I think, X coordinate, this is Z coordinate. This is my new action. I claim that this action has cost 1.
So let me understand what you're doing. You make a sequence of hyperbolic three manifolds where the Betti number is not growing to count linearly, but for which this generator is growing linearly.
No, it will grow sublinearly. So on the, if you would like to directly construct a sequence of subgroups, whose rank would grow sublinearly, you would take groups which are kind of go deeper and deeper in the Z direction and deeper in N direction, but not as fast. And they would have small generating sets because you just take generating set of subgroup of N and one generator here. So you're saving kind of in this direction. But the picture will also explain it. So yeah, cost of this X times Z comma mu cross tau should be 1. Why is it the case? So I will select some small subset of this form. So this will be, let's call it, maybe I should draw a bigger picture here. So I pick some small subset U, and U will be of the form X cross U0. U0 is subset of Z, and the only thing we want from U0 is that it's small. This measure is delta. And I now want to construct a graphing on this space that will connect every 2 points which are in the same orbit. So what I do is that I take the generating set S, which generates N. And because N is surface group for finite genus surface, I can find finite S that does this. And I put all arrows from S on this strip. Those will be all arrows. So my graphing will be S restricted to U for all S's in S. And I also add one arrow for every point, which goes in the Z direction. So plus sigma, where sigma is the generator of the copy of Z. Sorry, Z in the semi-direct product decomposition. So the sigma is put so we can kind of everywhere see the arrow corresponding to sigma, but the arrows corresponding to generating set of n, we put them only in the strip. Okay, and so if I were putting them everywhere, I would just get cost equal to the size of S plus 1. But because I'm putting them only on this small strip, the cost of the graphic I have just drawn is only delta times the size of n. So yeah, so the graphing is delta times the size of S plus 1. And because I can make delta as small as I want, I can show that cost of the whole thing is 1. Well, to convince yourself that this really connects all points in the orbit, you can just use this decomposition of gamma as the semi-direct product. So whenever I see point X and gamma X, suppose that for starters X is here, I can write gamma as some element of n times some power of sigma. So first I walk in the strip to generate this suitable element of n, and then I multiply it by appropriate power of sigma. So gamma is equal to n times sigma to some power. So I can do this, and because I can connect every point in U to any point in its orbit, to connect arbitrary two points in their orbit in the same orbit, I just first need to get back to U and then connect to the second point.
Okay. Having been trouble. Is this Benjamin-Schramm converging to what?
This thing,
yeah,
you can make it Benjamin-Schramm converge to the hyperbolic space. For that, you just need to kind of increase index in both coordinates, and that's enough. Well, yeah, you have to suitably take deeper subgroups of n and deeper subgroups of z, but this depth on the z direction is faster.
You will still get the 1.
You still get the 1, yes. So you still get the 1. So okay. So then okay, I think my motivation is just 4 minutes to get the result, but then I have to still. Okay, now why do I care about small subsets and how their geometry looks like? Because in every known construction of cheap graphings, it kind of looks like this. Not in the sense that we have product structure, but we have some small well-structured set on which we put some nice generators, plus collection of just single arrows for all the remainders that flow the space into this nice set. So to understand abstractions to constructing cheap graphings, we need to understand the geometry of small subsets of PNP actions. And in particular, because of this Albert-Weiss theorem, if we want to say disprove fixed price, we really want to understand the geometry of small subsets of the Bernoulli shift. And I can now state this theorem. So I should put up the preprint soon. I hope I do this before coming here, but I didn't.
It's probably going to do it in the second. The way he looks at his watch, okay, I'll put it on.
So now, okay. I think I just have time to state like approximate version. So
One more minute to state the full version. This is sort of the punchline. So
this is the punchline. Okay, so let me do this. Let gamma be a linear group. Assume gamma is finitely generated by some finite set S. And I claim that for every epsilon bigger than 0, there exists delta bigger than 0, such that for every
linear group, you mean lattice in a linear group or what's the linear?
no, just linear is enough. It doesn't have to be a lattice. This is like very abstract.
Linear means it's a subgroup of
It is okay. So it's countable subgroup of a algebraic.
Yeah.
Like,
For experts, I just need gamma to be exact, which is even bigger class. So, okay, for every epsilon positive, for every delta, if there exists delta positive, such that for every set U inside 0, 1 power gamma with mu of U. Mu will be just product of the x. So every sufficiently small subset. The set of returns to the subset will have a special geometry. So, just a minute. So there exists subset U prime, I know V, maybe let's say V inside U, with a measure of V which is smaller than epsilon times measure of U, so it's kind of much smaller than U, such that the set of gamma which bring back X V, sorry, to U without V is disconnected, has only finite components, and connected components in the Cayley graph gamma S. Maybe just what does it mean in human language? So I have this, let's say this is Cayley graph, and my return set looks like somewhat like this.
What generators? Any generator?
Any generators, but delta will depend on the generating set. So let's suppose that set of returns looks like this. Okay, or something like that. I don't know how to write it. Okay, this is the set of returns. And this theorem says that if this set of returns corresponds to a very small subset of U, it's a very small subset U, so you should imagine this set is kind of small compared to the occupies small proportion of the Cayley graph. And this theorem says that you can choose like epsilon proportion of the set. This will be V, make cuts here. And you will disconnect the set into finite pieces. And the set of cuts is very small compared to the whole set. So in particular, if you do this for a free group, it means that you cannot isolate a subtree of positive degree bigger than 2 as a factor of IED subset, even approximately, because in those sets you cannot cut them cheaply into finite chunks. So I have to add one more thing, that for this particular case of trees and free groups, there is another team of people, Hungarians. So Master, they kind of proved equivalent thing for free groups or gamma free. So my method works for arbitrary exact group, in particular linear groups, and also free groups. And it kind of, tells you that, put some restrictions on the geometry of those sparse factor variety subsets. I mean,
It's basically said that some strategy to create graphs of low cost for the supernullary would not work.
it should not work because I believe this result will be, it's very useful if you want to disprove fixed price because it kind of restricts what your graphics can do. But there is still a long way to prove, to disprove fixed price for hyperbolic groups because whatever you can do, hoping to disprove it, it should not work in higher rank. So you should hunt for purely hyperbolic phenomena, right? And I think this will be very useful. I think for kind of factor variety community, this is independently useful, like regardless of application to cost, because in the abstract I talk about local algorithms. I didn't have time to do this here, but this kind of puts restrictions of what kind of subsets can be distinguished by a local algorithm on a group. And I think I should finish over time already. Questions?
How do you choose this V?
How do I choose this V? So the proof tells me that I can I'm guaranteed to find constant proportion of pieces of my set that look like that have small boundary. And I kind of iterate that. Whenever I see a piece of small boundary, I cut it out from the set and do it again. And with some work, which by the way, I use some result that kind of tells me that this is enough by Schramm, I can find this concept. So it's enough to.
So which result to Schramm are you using?
That's
the ingredients of your recipe.
So the result of Schramm I'm using is that if you have a sequence of graphs that converge Benjamin Schramm to hyperfinite graph, then they are approximately hyperfinite. And this thing I wrote here is definition of approximate hyperfiniteness.
How do you use its linear?
Linearity is just used to say that gamma is exact. And exact means that it admits topologically amenable action in a compact space. This maybe to how can I say it intuitively? In exact groups, finite subsets have special geometry. Let's say like this. In non-exact groups, you can take a sequence of finite subsets of your Cayley graph, and in some sense they could limit to something which is very non-amenable. In exact group, this is impossible. Like when you take a sequence of finite subsets of a Cayley graph, any Benjamin-Schramm limit of the sequence has to be amenable. This is exactly.
All right, you said that linear implies exact and some other things. How do you use this linear? I'm just curious. And
this is
whatever the other property that
linearity.
I mean, where do you use it? The matrix that they.
So I'm only using exactness.
Some theorem that linear is exact.
Yes, there is a theorem by Weinberger, Sharp. I forgot. Shmuel is definitely one of the authors. They proved that linear implies exact. It's very deep, and I just wanted to stay linear because I didn't expect that many people would know what exact groups are. But lattices and semi-simpler groups are exact. Mapping class groups are exact. You have to work hard to find any example of non-exact groups, and Gromov suggested the probabilistic construction, which was then completed by Saida, construct examples of non-exact groups.
What is used in the proof that a linear group is exact?
I don't know.
I don't know, but you say it's deep.
I think, okay, because it's about the existence of some nice action, some nice boundary. I suspect that linearity provides you natural candidates for this action.
Okay, but what's the deeper? Or
What's the deep thing?
no, you just said it's deep, so I'm just
I
wondering.
think proving that it's topologically amenable
Okay.
is deep. Right.
You said that to get a nice rate for the vanishing, you could maybe use some number theory. Can you say a little bit more about what kind of number theory could be used?
Well, I can tell you that okay, so in SLDZ, when you take congruent subgroups, you can find explicit generating sets of size roughly log index to some power. And I'm not sure this for this group, I wouldn't say it's particularly deep, because what you're using is that if you have unipotents here, you can kind of act by, well, sorry, what do I want to say? I have a unipotent matrix here, right? Some unipotent matrices. How can I quickly generate many more unipotent matrices? I don't want to say something stupid. Okay, I'll give you a reference to a paper. Lubotsky. They work it out for non-compact arithmetic lattices. How can you find small generating sets? And it uses some number theory. On kind of in a different direction, if you have higher rank lattices, you can hope to use Norrie conjectures to find small generating sets. But I'm not sure. I mean, maybe you can ask me later, because explaining this would take at least 10 minutes.
Okay, we can do it.
Other examples where can you give me an example where you need V, where you have infinite connected components?
Yeah. So where you need V. So let me think for a moment. It's hard to kind of think about. Okay, so let's see. You can, okay. Do you believe that you can get Galton-Watson trees as a? Okay, in a free group, I can kind of construct my set U in the following way. That okay, first I select just the first example that I showed today. So I select I just require one coordinate to be between 0 and delta, and this selects for me a sparse family of points. And then I can enlarge this set so that I'm adding balls around those points. Okay. And I kind of pick the parameters so that you expect those balls to barely touch. So each ball has, I don't know, 3 neighbors that touch it. And then you prune away the branches that are not used in those connections. Okay, I worry that it's not visible how you do this on level of the action on Bernoulli, but it's anything that you can do by algorithm that looks at random labels at the vertex and decides whether they are in the set or not can be realized in this way. And in this way, you can kind of construct a subtree of a Cayley graph of a free group, which has long bridges it has some branching at some points, but most of the subtrees are just long lines. And then this cut set would need to cut those lines at some point. So again, this is the example that we need this. So you can get infinite connected components, even if set U is very small. It's just most of the time they will look like either long lines or a interior of a ball, something like this.
Okay. If there are no more questions, let's thank Mikołaj.